The consensus among most scientists is the Big Bang Theory, which is the leading explanation for the origin of the universe, which includes the creation of stars, planets, and all life on those planets, including ourselves. Despite its somewhat whimsical name, the Big Bang offers a descriptive glimpse of what might have happened. At first, the universe was compressed into a small space, smaller than the head of a pin, where the particles were tightly packed. A huge explosion of matter followed from this tiny speck. This event, known as the Big Bang, took place billions of years ago and set the stage for the unfolding of cosmic history. However, the development of scientific knowledge led to increasing conflict with the predictions of the Big Bang Theory. When NASA launched the James Webb Space Telescope, the largest and most advanced space science observatory ever built, scientists expected that its observations would confirm the Big Bang Theory. Unfortunately, after only 1 year in space, the telescope amazed scientists with its unprecedented ability to peer deep into the universe's past. The remarkable capabilities of the James Webb Telescope have revealed galaxies so ancient that they challenge our understanding of the origins of the universe. This revelation sparked intense research into what existed before the Big Bang. One of the turning points in this search occurred when Rohan, an astronomer working with the data from the telescope, found a galaxy that dates back only 300 million years after the Big Bang, making it the oldest galaxy ever observed. Rohan's discovery sent shockwaves through the scientific community, highlighting the transformative potential of the James Webb Telescope. Its mission to revolutionize our understanding of the cosmos has just begun, and it promises to reveal unprecedented insights into the earliest epochs of the universe's existence. This era, which was almost unexplored before, is the key to understanding the formation of the first stars and galaxies. The findings of the telescope contradict initial expectations and revealed galaxies with properties that exceed previous predictions. This unexpected abundance of early galaxies sparked a flurry of research, challenging scientists to reconcile these observations with existing theories. As scientists grapple with these discoveries, they face profound questions about the fundamental nature of the universe and the forces shaping its evolution. In addition, the technology of the James Webb Telescope is revolutionary. At 1.5 million kilometers from Earth, shielded from terrestrial interference and cooled to near absolute zero by a tennis court-sized sunshade, the telescope carries a giant segmented mirror and extremely sensitive instruments designed to reveal unprecedented detail of the cosmic dawn. Known as the Cosmic Dawn, this era occurred just a few 100 million years after the Big Bang and marked the period when the first stars and galaxies began to form. Its evolution process is still the subject of intense research, with theories ranging from the influence of dark matter and dark energy to the interaction of starlight, gas, and dust. The galactic observations of the Cosmic Dawn Telescope offer cosmologists a unique opportunity to test their understanding of these fundamental phenomena. By studying these ancient galaxies, scientists can either confirm the validity of their current models or reveal pockets of understanding that could lead to profound new discoveries. Initially, the telescope was expected to find only a few faint and small galaxies during pilot studies. However, the reality exceeded these expectations. The telescope's first images of the distant universe revealed many galaxies whose age, size, and brightness exceeded all predictions. This unexpected abundance of early galaxies has sparked a race by astronomers to set new records for the earliest known galaxies. Every day claims a new record discovery that leaves the scientific community in awe and forces us to reevaluate our understanding of cosmic history. Since the discovery by the James Webb Telescope, theorists and observers alike have sought to explain the existence of these unexpectedly mature early galaxies. Some speculate that these anomalous findings may be due to errors in the telescope's analysis of the initial observations. However, the consensus is that these observations represent a paradigm shift in our understanding of the early universe and offer intriguing clues about the nature of cosmic evolution. Recent revelations about early galaxies from the James Webb Space Telescope raise profound questions about the nature of the universe and challenge the assumptions of standard cosmological models. Some scientists speculate whether these observations can be reconciled with existing theories, while others suggest that they may be the first signs that the universe is even more complex and strange than previously imagined. At stake is nothing less than our fundamental understanding of how the ordered universe as we know it emerged from primordial chaos. JWST's early discoveries could rewrite the opening chapters of cosmic history, shedding light not only on distant ages and distant galaxies, but also on the existence of our own Milky Way galaxy. AS European Space Agency Science and Research Advisor Mark McCarran aptly said, "You build these machines not to reinforce a paradigm, but to break it. You just don't know how it's going to break." JWST's origins can be traced back to the Space Telescope Science Institute in 1985, even before the launch of the Hubble Space Telescope. G. Weilinger, then the deputy director of the SDSCI, was tasked with envisioning what would happen after Hubble renamed JWST a former NASA administrator. Unlike Hubble, which primarily observes visible light, JWST is designed to observe in the infrared spectrum, allowing it to look deeper into the universe. This ability is crucial for studying early galaxies whose light was extended into the infrared by the expansion of the universe, making them invisible to telescopes like Hubble. With its large, cold star-like mirror, JWST has become the perfect tool to unlock the mysteries of the cosmic dawn. The need for JWST was highlighted in 1995 when the Hubble Deep Field Survey revealed a cluster of galaxies in a previously empty patch of sky. This discovery hinted at the richness of the early universe and reinforced the importance of a telescope that can delve ever deeper into cosmic history. After more than 2 decades of development and a cost of about $10 billion, JWST was finally launched on Christmas Day 2021. By July 2022, it was ready to begin its first year of scientific observations. Early programs such as the Cosmic Evolution Early Release Science Survey and the GRISM Lens Amplified Survey from Space were designed specifically to search for early galaxies. Although initial expectations were modest, the results clearly exceeded predictions. JWST observations have challenged existing understandings of the early universe, revealing galaxies that defy conventional models. These unexpected discoveries highlight the limits of scientific research and highlight the transformative potential of cutting-edge technology like the James Webb Space Telescope. As scientists continue to unravel the mysteries of the cosmos, they are poised to rewrite our understanding of cosmic history and the forces that shaped our modern universe. Early observations from the James Webb Space Telescope stunned astronomers by revealing very distant galaxies.
Almost immediately before JWST, the most distant known galaxy was GNZ 11, discovered in 2015 at a redshift of 11, corresponding to a cosmic age of about 400 million years. But as JWST observations began, the GLASS team, led by Rohan and another independent group, made a remarkable discovery. They identified a galaxy called GLASS Z13 at a redshift of 13, about 70 million years earlier in cosmic history than GNZ 11. The rapid pace of these discoveries was facilitated by simplified redshift estimation techniques, which, although less precise than direct measurements, provide a quick estimate of the galaxy's distance. Surprisingly, GLASS Z13 looked unexpectedly bright and massive, already having the stellar mass of billions of suns, despite being significantly younger than the Milky Way. Later observations revealed even more surprising results. Dozens of galaxies appeared with an estimated redshift of up to 20, suggesting that they existed only 180 million years after the Big Bang. Some of these galaxies had disk-like structures that were not expected to occur so early in cosmic history. Additionally, there was evidence of galaxies comparable to the Milky Way at redshift 10 less than 500 million years after the Big Bang. These rapid developments challenged the predictions of the standard model of cosmology, the lambda cold dark matter model, which describes the evolution of the universe based on our understanding of dark energy and dark matter. According to this model, galaxies of this size and luminosity should not have formed so early in cosmic history. The formation of massive galaxies in the early universe is a great mystery to cosmologists. To solve this problem, it is necessary to understand the early stages of the evolution of the universe. In the first seconds after the Big Bang, the universe was a hot, dense soup of eternal particles. Over millions of years, the first stars began to form, creating the building blocks of galaxies. This process of cosmic evolution from a chaotic beginning to the structured cosmos we observe today is believed to have taken about 1 billion years. The JWST observations challenge this timeline, revealing galaxies that appear too mature for their cosmic age. Rather than seeing many small protogalactic fragments merging into larger galaxies, as current models predict, JWST observed galaxies that are already large and bright. Subsequent observations with instruments, such as the Atacama Large Millimeter Array in Chile, provided further evidence for the authenticity of these distant galaxies, ruling out the possibility of low redshift intruders. These groundbreaking discoveries open up new ways of understanding the early universe and may require a revision of our current cosmological models. JWST continues to change our understanding of cosmic history, challenging our preconceptions and pushing the boundaries of astronomical research. The lack of detectable dust from the observations of the Atacama Large Millimeter Array highlights the challenges telescopes face in confirming observations made by the advanced features of the James Webb Space Telescope.